Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Come on. Is that dead? Oh, jeez. All right, so in the meanwhile, I'll talk about the assignment, which will be given up tomorrow. All right, you have 2 weeks to complete it. I think that's enough, right? And if I give you more time, you just do assignment of other classes. It ends up the same thing. All right, I think today we actually have the room booked for more than 1 hour. So if you already downloaded the lecture notes before, there's an updated version online now. You should update your notes. This computer's not cooperating. Maybe I should use my own. So. Fine. Let's see if this works. All right, maybe I can use this one. So lecture slides. Okay, so I believe that's where we are from yesterday. Right, so this is a function to sort of calculate the multiple period variance, right? And we said in the long run, if return can be approximated by this predictable return in expected terms, the long run return is smaller, right? That's where we were. So this is from this book of long run investing. So yeah, so we were talking about a lot of investment advisors, including those robotic advisors, which really is having the program behind it. They could recommend to sort of hold a long investment horizon. If you have a long investment horizon, then they recommend you hold more of the risky assets, such as equity, right? So when behind all these models, you should realize they're sort of assuming the long-run return is mean reverting, right? So it's predictable in expected returns. So how do we sort of show this. So I think you already have the basic model to actually build up how much to invest in equity shares, given your utility function, given the stochastic process of the returns, right? So just go back to I think lecture 2, right? So lecture 2 we talked about the utility, the expected utility, right? And what's to maximize criteria is to maximize your expected utilities, not utility of expectations, right? So because of this expected utility function is concave, right? So maximizing expected utility will give you actually the optimal asset allocation in terms of how much to invest in stocks versus risk-free rates. Right, so what I here do have is just to define my utility function. Right, so this is just, as you see, the power utility curve. Right, so it's final wells times, or actually time times, so this is to the power of 1 minus gamma, then divided by 1 minus gamma. Right, so what's my final wells? Final wells is just my 1 minus the share in the risky assets times the risk-free rates, plus this S, which is the share in the risky assets times the returns. I have this W0 here, but that W0 doesn't really matter because, by the way, what is this power utility curve? Is that constant absolute risk aversion or relative risk aversion? Power utility is constant relative risk aversion, right? So as long as we know gamma, we can calculate the shares of this risky investment regardless of W0. Right, so I can just set whatever W0 I want. And if you sort of look closely, one difference is usually you have 1 plus R, remember, right? So why I don't have 1 plus RF, 1 plus risk asset here? Because usually, right, you have this return then 1 plus share S or alpha times 1 minus, 1 minus alpha times the risk-free rate plus alpha times the risky assets, right? But here I don't have risk-free rate and the risky assets. What happened here? Anybody know? So what's this np.exp? np is numpy, right? What's exp function? Exponential. So why do I have exponential function there? Because my returns are logarithm. Remember that? So if you look at this, my returns, they are logarithm. Right? So if you have logarithm, what's the advantage of that? If I want to calculate a multi-period return, I can just sum up, right? So it's 1 plus logarithm plus logarithm plus logarithm is just 1 plus R1 times 1 plus R2 times 1 plus Rn. Same thing, right? So, but what I get is 1 plus R ampere return. Okay? So to get the Rn, I really need to sort of exponential it, right? To get to the 1 plus R. So that's why I write np dot exponential. If you sort of forget that, use 1 plus R. I mean, it won't be, very off because the log approximation usually works quite well. but it's not really correct. Then finally, I have this multi-period return, right? As I said, it's just the sum because I have log return already, right? And depending on how many periods, so the period is just how many rows I have, so that's why it's shape 0. It's the rows of this return array. And the risk-free rate, we assume it's constant, so it's just k times the risk-free rate. Okay? So, you know, with these three functions, we can actually estimate the return, the asset allocation. Right, so for example, let my possible choices of shares to be lie into this space of 0 and 1. Right, I'm just picking 100 value from 0 and 1. And my return array is just normal with mean mu and standard deviation sigma. So sigma times this standard normal plus mu, that's my normal distribution of mean mu and standard deviation sigma. And what's the dimension of this random variable? On the first dimension, I take how many periods they have, k periods. And on the second and the third dimension, I want the number of samples. Right. I mean, I can just use two dimensions, like one dimension with the k periods, second dimension with number of samples. I want to sort of have three dimensions so that program runs quicker. Right. So if you notice, my number of sample is 1,000. And because I have these two dimensions, so that'll be 1,000 times 1,000. So my simulation runs 1,000,000 times simultaneously. Right? So that's my return array. And from this return array, I can calculate, just use the function before, I can calculate what's my risk-free rate, what's my risky return, given this multi-period return. Right? Now what I need to is just to, for every allocation that lies in 0 and 1, I want to calculate what's the future wealth. And from this future wealth function defined before, I can calculate what's the utility given the wealth and my gamma. Gamma, I take 5 here. Right? So I can just calculate all these and then take the mean. Because I have two dimensions, I take mean and then take mean. So that will be my mean of simulated utility. So that's my expected utility, right? Given any of the allocations. Then I just put them into the table and look at the share that's maximizing. So IDX max, that gives my maximizing expected utility. And I want to plot them here. Right, so my maximized expected utility, about 60%. That's as what we talked about before, right? And this curve just gives us the expected utility curve, given the different shares. Right? So this is just one horizon, right? But multiple periods. Now I want to see if my horizon changes, would this best allocation change or not? Right? So I just have this multi-period ID utility allocation. Everything else is the same. The only difference is that now I want to change this k period. Right? Change the number of periods starting from 1 to whatever number I want. Right? So if I look at the long horizon allocation, given this period is from 1 to whatever number, I pick 30 here, right? I can calculate the optimal allocation as the program gave us before, and then I just asked the program to actually plot it, the optimal allocation. As you can see there, the optimal allocation actually stayed the same. If I change my horizon from 1 period to 30 periods. Okay? So that tells us with the RID distribution, the investment horizon doesn't really matter in terms of SL allocations. Every time we get the same optimal allocation. That's because returns are identical, distributed, and they are totally independent. Okay? Now, if the returns, oh, sorry, there's something else here. As I talked to you, well, we can calculate this with the analytical solution, right? Remember, analytical solution is expected mean excess return divided by gamma times sigma square. That's what I think what we learned in week 3, right? Now, with ID returns, we know that the mean and the variance are growing at the same rate, right? So the mean is growing at the rate of k, when the horizon represented by k increase. And the variance is also growing by k, as we see from yesterday, right? So if variance of k period return equal to k times the sigma square, then the top and the bottom are growing at the same rate in this top equation, right? So given that, we know the solution must stay the same. So not only we can sort of solve it using the simulation, we can also solve it analytically to show you that if it's ID, the optimal allocation really doesn't change with the investment horizon. Right. So by the way, now can you guess, just looking at this top equation, right? That's the solution for our optimal allocation. So now if the returns are predictable, how would the optimal allocation change? Increase? Why increase?
Because the variance is both less than k. So it's like the denominator is less than k, so smaller than k, so it's kind of like, the range that is harder.
Okay, so on the top, the mean return grows still at the rate of k, right? As k period, the mean return is k times the expected return. On the bottom, gamma times sigma square, but the multi-period sigma square, as I showed you yesterday, is less than the k times 1 period variance. Right? That's because the covariance of the returns, realized returns, that they are negatively correlated. Okay, so if you have predictability. So the top is growing at the rate of k, the bottom is growing at a rate less than k. So as the solution shows, this solution should increase as the k increase. All right? So we can also sort of show you what the solution is. So this is actually correlated utility allocation is another function because I use the sort of a shortcut of predictability. So I don't want to sort of bother you with the programming detail of this, right? So you can see this is horizon equal to 5. The optimal solution is 0.54. If horizon equals to 60, the optimal is 0.53 before. Now increase to 0.54, right? And you have a bunch of ways to actually do this. One obvious way, so this is a shortcut. This is actually not completely following what we talked about from yesterday. One thing to program up is Remember yesterday I showed you this simulation of two variables that's correlated negatively, and the RIT is your XIT plus a random variable, right? Somewhere there. Here we go. Right, so you have this, specify this covariance structure. With this covariance, you can generate the correlated errors using this random multivariate normal function. Right, and then to simulate to process, you have this XI process, or XT process, actually, I can call this T, and RT process. Right, so with this structure of the returns, then you can just use the multi-period function I showed you in the ID case to generate the asset allocation when the returns are correlated. Right? So instead of bore you with those technical details, which you might actually think, my complaint is this class is already too hard. I don't want to give you more ammunition to complain. So you can look at, where is it? Did I miss something? Here. You can look at, this is the picture from this paper by this author Barbaros in 2000, I think, in Journal of Finance. Right, so he estimates that the allocation, the percentage allocation to the stocks, so the best solution should be sort of increasing when the horizon increases in years, right? By the way, what he used is using sort of more complicated VAR process, as we talked about in the last week. Last week talked about VAR of DP predicting the returns, the DP predicting the future DP, right? So he used this VAR and it generates a predictor from that VAR system, and to just got this plot. Right. But this is to just use sort of the point estimate of the predictability, right? But we know that this predictability, although it's there, but it's not that strong, which means R squared is small, and the confidence we have, or the error term we have, will grow as we move to longer and longer future periods. All right, so if you sort of use the VAR to estimate one period term, and you use the VAR to estimate 10 period term, the error band will grow if you know statistics, right? So the confidence interval will grow as the prediction goes to sort of longer future periods, deeper in the future, right? So if you consider that estimation error increases with the horizon as well, right? Then the optimal solution is no longer just straight going up. At some point, it will actually goes down because the uncertainty in estimation dominates the predictable return effect. All right, so although you see that all these websites give you, if your sort of key investment horizon is very, very long term, they suggest you to sort of invest hugely in the stocks, but that's sort of assuming, we have the mean return and we don't really sort of care about uncertainty in predictions, okay? And, if you go to sort of any sort of investment website, they will tell you if you're saving for retirement and you're young, like 30 years old, a fresh graduate after school, they suggest you sort of invest 80+% in the stocks. But if you are sort of old like me, then you invest less, right? Okay. So what is this? Okay. So now this is what we sort of get sort of empirically, right? And using simulation and using the optimal solutions. But how can we sort of more deeply understand why the optimal allocation actually increases with the investment horizon? Right, so one such theory is called I-Taipan, the intertemporal Taipan. Right. So remember what we did before is just to maximize one period expected return, right? Now you are maximizing sum of many one period expected returns. Okay, so you care about all the future returns. So one way to sort of shortcut the problem is to assume there is a value function that's your optimized utility, right? And now this value function not only depends on your wealth W, but it also depends on something else called Z. So how do we sort of interpret Z? Z is like your investment opportunity, right? Or state of the world. So in the future, not only your wealth will change, but the state of the world investment opportunity will change. Right, so I can characterize this optimized value called the value function as this V of WZ as just two problems, recursive problem, right? It's the maximize the current utility plus beta, which is the discount rate, times the next period's net maximized utility. Right, so this is actually called sort of Bellman equations, which means if everything is maximum at multi-periods, it must be true it's maximum for me in this period, and it's maximum for me in all the future periods. But if horizon is infinite, all the future periods is just like today's all the future periods. Right? Will be the same as the value function itself, maximize the utility itself. Right? So the way to actually solve this is, again, take the first order condition. You write the what's called Bellman equations. Right? So the marginal utility, so V of little v, V of this V at the subscript, that means that takes the partial of your utility function with respect to your wealth. So it's marginal utility of your wealth equals to discount rate beta times the expected marginal utility in the future, in the next period. Right? And in the next period, because your utility should have this return also, so that's why you have this beta times expected VW times the RT plus 1. Right? So I used to sort of teach students how to actually derive this, solve this, but I think this is probably too much for you guys. So I just presents the conclusion for you. Okay, so the shortcut is that you can sort of derive this function, solve it. The solution will look like something like this. The expected excess return equal to beta times the expected market return plus a new beta, I call the beta I adder, times the expected some premium of eta. So if you look at this equation, up to here, it's the same as cap m, right? Now you have this extra term. What's this extra term? The extra term expected RE of eta t plus 1, that's the risk premium for your changing of future investment opportunities. So for example, if the future market return will be higher, you want your beta to be higher at that time, right? But if your investment beta is actually lower, when the future returns higher, that's a risk for you, right? So to really sort of optimally grab the opportunity in the market, you want to invest in highly risky assets when market is really good, right? But you are not, God, right? You don't really know this. So this actually is a risk for you. Maybe you don't have the right beta when the market is good. So this second term represents this so-called future investment opportunity risk. Right, so which means not only my return should be correlated with the current return of the market, that's the beta, usual beta you have, but also should be correlated with all the future investment opportunities. Right, so sometimes we call this eta the maximum hedging portfolio. So the question is, what is a good hedge that can hedge me against such future risk of investment opportunities? Right, so what's a good hedge for this? So if you just read the slides, you will know, oh, okay, I said the market portfolio is a good hedge against its own investment risk. But why is that? Why the market portfolio itself can be a hedge portfolio for this second term, beta times expected R of eta. Beta. So what's my really risk? What do I worry about? Yeah, so I worry about maybe at some time the market return will be really, really low. Or when the market returns high, my beta is actually low. Right? So what's my solution for that? I just hold more of the returns or more of the market portfolio so that I jack up my beta, right, to sort of take advantage of when the future beta is high. But what if when the future returns high? But what if the future returns low? Well, remember the returns are actually mean reverting. So if the future returns low, at some point, actually it will be really high. Right? So if I really sort of want to hedge against this risk of my future returns at some point will be low, I want to take advantage of the periods my return actually really is high. Understand this? Right, so you want to hedge more portfolios or more of this market equity, more market portfolio to actually take advantage of the periods that my future returns are really high, to offset the risk of periods that my future return is really low. Right? So the market portfolio itself is actually a natural hedge against this risk of future returns really low. Right, so the indication here is that if my investment horizon is long, then I should hold more stocks larger than what's called the myopic investment demand. Myopic meaning I only look at one period, right? Very short-sighted. So the intertemporal campaign also tells us that when the investment horizon increase, I should hold more stocks to offset the fluctuation in the future investment opportunities. Therefore, I should actually hold more of the equity in our optimal solutions. Okay, so we talked about this. That's a fun topic. That's very controversial, right? So if you really believe the market is actually predictable, at least in the expected returns, not in the realized return, right? Then you should be able to do some market timing. Right, so how do you do the market timing? The easiest thing is just when you expect the market return to be high, you hold more of the equity. When you expect the market return to be low, then you hold less of equity. Right? So this market timing really depends on your ability to sort of predict the future expected returns. Right? So instead of just buy and hold, if I have the ability to do the market timing, then my optimal investment allocation line should be upward sloping. Right? So in the sort of unpredictable RID world, you end up with this green line. Right? So buy and hold, regardless of period, regardless of the long-run mean return or expected excess return. But if you sort of believe market is predictable, then the timing should be, market timing should indicate that your allocation should be upward sloping, means that you hold more of the stocks, right, allocation to stocks, when the expected return is high. But that doesn't, this doesn't really require you to be a sort of far-sighted investor. If you only care about one period return, you should do this, right? But if you care about more than one period return, your investment horizon is high, that's called if you're a strategic investor, then your whole investment should shift upwards, holding more of the equities. Right? So, well, let's see if this is actually easy to do. So let me just use a very simple strategy. Right, so if the predicted excess return is positive, then I'll invest in risky assets. If the predicted excess return is negative, then I'll put everything in the risk-free rate. Right, that's easy enough, right? So I can use the model that's using the DP to predict the expected returns, as we said from the last period, and then just do my investment according to that rule. What you end up is this blue line, the market timing line. Well, you'll say, oh, market timing is not great, but sort of works, right? But actually, I was cheating. Where was I cheating, and what's the correct way to do it? So what I did is to use the DPR regression model to estimate the predictable coefficient, right? Then use this coefficient to get the predicted market returns each period. And then, according to this predicted market return is positive or negative, I put my assets into risky asset or risk-free asset, and I plot this line. And I told you that's actually cheating. Well, if you're an investor that's trying to invest in 1980s, do they have the information of the whole time series of this graph? No, right? So what I did is actually fitting the model in sample, which in investment, I think sometimes people actually call it looking ahead bias. Right? So you are using the data that's looking ahead to actually estimate your parameter. And when you do this, your model performs better. What you should really do is like your assignment. Right? Remember, in your assignment, you are doing what's called back testing. Right? You are using the information only up to that point, and then follow your strategy and have the information rolling either with an expanding window or with a shifting window, right? So you're rolling your information window and then do it period by period to see how your model performs, right? So I don't have it here, but I can tell you if I follow this back testing correct strategy, the market timing strategy that's just using the GP performs much worse than this. All right, so there's a huge debate in the literature. Therefore, the market actually is predictable, or what should be the predictive variables? How much, especially how big the R square is. It is. And this is sort of ongoing literature. But that doesn't really mean actual investor in the market cannot do the market timing. Right? It's just that we, as a researcher, we are not smart enough. Or we don't really know all the information the real investor in the market knows. Right? So how do we actually see if the real investor in the market are actually be able to do the market timing or not? It's very easy, right? You look at the beta. As we said, if you are really trying to do the market timing or you are trying to offset the risk of changing market opportunities, then what you really should observe is you should hold more of the risky assets when the market is good. So your beta should increase with your market return. Okay? Or in a more simple strategy, your beta should increase when market is positive. Okay? So the first one is what's called a channel strategy. So you can estimate your beta at the time t with respect to the return of the market. So if you have market timing ability, this